Welcome to Lecture 11, in which I'm going to introduce two very big new ideas in physics, the ideas of work and energy. You'll remember back in Lecture 2, when I talked about languages of physics, I mentioned a number of terms that we tend to use in everyday life that have more precise meanings in physics, and work and energy are two of those very important ideas. So I'm going to begin by defining what physicists mean by the concept of work, and I'm first going to do it sort of loosely, and then I'm going to do it more precisely. So work, the essential idea is this. Work done on an object is the product of the force you apply to that object times the distance the object moves. So work is about force and distance, or force and displacement, force and motion. If an object doesn't move, you can be applying a force to it, but no work gets done. Work is the product of the force applied to an object with the distance it moves. Now that definition isn't quite accurate enough, so we've got to get a little bit more precise. Work is the product not just of the force, but of the component of the force in the direction an object moves, multiplied by the object's displacement. So there's another issue here, angle between the force and the motion. If the force is in the direction of the motion, then the work is just the product of the force with the distance the object moves. If the force is at some angle, you have to figure out the component of the force in the direction of the motion. Let me do a couple of examples to demonstrate what I mean by that. So here's a big, massive bowling ball. It's got a lot of weight. If I want to hold this bowling ball, I have to apply an upward force to it to counter gravity. If I don't apply that force, it's going to fall. So I'm now exerting a force equal to the bowling ball's weight. I'm exerting it upward. The bowling ball isn't going anywhere, and so I'm not doing any work on it. And now I'm going to carry this bowling ball across the set here. Heavy bowling ball. But as far as physics is concerned, I'm not doing any work. Why? Because the force I'm applying to the bowling ball in this case is upward, and the bowling ball's motion, as I carry it along, is entirely horizontal. So I am not doing any work as I carry the bowling ball along the floor. No work. Because the product of the component of the force in the direction the ball is moving, the horizontal direction, is zero, because the force I'm applying is vertically upward. On the other hand, if I do this, then I've done work on the bowling ball, because then the force is in the same direction as the motion, and the work I've done is simply the product of the force I exerted times the distance the ball moved. If I take an intermediate case, if I take the bowling ball and I move it, say, diagonally like this, then I'd have to figure out what component of the force I'm applying is in the direction in which I'm moving it. So work is basically force times distance. That's a good way to kind of remember what it means, but it's a little bit more precise. It's the product of the component of force in the direction something moves with the object's displacement. Now, why is this at all important? Sounds like a rather arcane mathematical idea. It's important because work is related to another quantity in physics which is of crucial importance and which you know of very well, and that's the quantity energy. Work and energy, as we'll see in this lecture, are intimately related. So let me say a little bit more about work. Like any physical quantity, it's got to have a unit. So what's the unit for work? Well, the unit for work is the joule. And the joule is named after James Joule. James Joule was a brewer. He was interested in replacing steam engines with electric motors back in the 19th century. He's best known for having figured out what's called the mechanical equivalent of heat, the energy equivalent of a certain amount of heat. He basically showed that heat, and I'll define that term more precisely later, that heat is a kind of energy. He showed that electrical and mechanical work were both equivalent to certain amounts of heat energy. So he was very much involved with energy, and the unit for work, and indeed the unit for energy, it's the same unit, is the joule. And following the conventions I mentioned earlier when I introduced the Newton as the unit of force, the joule is abbreviated with a capital J, that's its symbol, but when we write out the term joule as the word for the unit, we write it with lowercase j. So James Joule was a physicist who worked out this relationship between heat and work and energy. And so the unit of work is named after him. And if we want to get the unit of work down in its basic SI, System International terms, a joule is a Newton meter. That means if I apply a force of 1 Newton and I move something through a distance of 1 meter, then I have done, by definition, 1 joule of work. So that's what a joule is. So here's a picture of James Joule, and on the right you see the apparatus that he used to exert mechanical forces on water in a closed container, and by stirring it and agitating it vigorously, he was able to show that the mechanical work he did ended up heating up the water, and he was able to measure quantitatively that relationship. We'll see more about that when we get to section 3 of the course about thermodynamics. So that's James Joule. Let's do some very quick, simple examples of work. So, simple example. You got a stalled car. You're trying to push the car. So here you start out. You're going to apply a force of 400 newtons to this stalled car. You're going to push it at a distance of 6 meters, about 18 feet. So there we are afterwards. We've exerted a force of 400 newtons. The force is in the same direction as the car moved. Work is force times displacement. More precisely, a component of force in the direction we're moving, but in this case, they're the same. And so that's 400 newtons times 6 meters is 400 newton meters, or 2,400 joules, 2.4 kilojoules. So that's how much work this person did in pushing that stalled car 6 meters. Push the car farther with the same force, would have done more work. Apply a greater force over the same distance, would have done more work. Another example, lifting a bowling ball. Bowling ball has a mass of about 7 kilograms. So here we are lifting the bowling ball 1 meter. This one's just a hair more complicated than the previous one. We need enough force to counter the ball's weight. Let's assume we lift the ball with constant speed. So we aren't accelerating it. We're just lifting it with constant speed. If we lift it with constant speed, the net force on it is 0 because it's not accelerating. F equals ma. A is 0. F net must be 0. We need enough force to counter the ball's weight and no more. Well, the ball's weight is mg, so the force we need is mg, 7 kilograms, times 9.8 newtons per kilogram, that other way of expressing the gravitational acceleration. That's 69 newtons. So now we know the force, and we're going to exert that force over a vertical distance of 1 meter. As the ball moves vertically, it's going to be a vertical force, so the force and the displacement are again in the same direction. So we're going to exert 69 newtons for 1 meter, and we will have done 69 joules of work, quite a bit less than it took to push that stalled car, the 6 meters we pushed it. So those are two very simple quantitative examples of doing work. Those were simple examples because in both cases the force was constant. It didn't change with time. It didn't change with where I was in the push. But often we have situations involving gravity, at least over large distances, situations involving springs, and a number of other situations where forces may vary with position. And I want to show you mathematically how we handle that situation. And I want to do it quantitatively in one simple case, although in most cases you have to use calculus to deal with that in all its quantitative detail. So let's take a look. Here is a force that varies with position. On the horizontal axis, I've plotted position. On the vertical axis, I've plotted the force F, and I've written it explicitly as F of X to say the force depends on position. So it started out small, it got bigger, it got smaller again, and I want to know how much work would be involved if I applied this force as I moved an object from one position to another. Well, here's a way of getting at that. I can think of a small part of that path from here to, say, here, as a little piece of it, delta x I'm going to call it, a little change in position, delta x. And during the time I'm moving over this little interval, delta x, the force is approximately this value, F1. Not exactly, because some of the time it's a little bit below it, some of the time it's above it, probably it averages a little bit more than my F1, but it's approximately right. So what I do is I say, okay, for that brief interval of position, I applied this force F1, and therefore the work was approximately F1, the force I applied, times that interval delta x, that displacement delta x. And then I say, okay, later on, I go another interval delta x, where the force is now approximately F2 marked here, and I calculate the area of that rectangle, the force times the displacement, and that gives me the work it took to move from here to here, the second interval delta x. And then I do that for more intervals. And when I add up the areas of all those rectangles, I'm going to have something that approximates the amount of work I did. It's not a very good approximation with these rectangles, but I can make it better by making the rectangles smaller. And if you were doing this problem on a computer, you can imagine dividing this area up into hundreds or thousands of rectangles and making that get pretty accurate. Well, The branch of mathematics called calculus tells us how to do that exactly without having to go through the cumbersome process of dividing up into rectangles, and I'm not going to do calculus here, but the fact is that if you get the calculus answer, or if you approximate it with those rectangles, the work ends up being the area under the force versus position curve. Keep that in mind because we'll use that again later when we understand, for example, how gravity works over large distances, and we try to figure out the work done to move against gravity, to move a spacecraft a large distance, say, from a planet, or to see if something can escape a planet's gravity altogether. So work is the area under the force versus distance curve, the force versus displacement curve. One particular example of a force that varies position is the force associated with a spring. Springs stretch, and they exert forces. And it turns out that for springs that are reasonably well behaved, the more you stretch the spring, the greater the force. To quantify that, we introduce for the spring a quantity called K, the spring constant. And the spring constant tells you how much force you get for a given stretch. So what I have here are several springs that I want to look at and see what their spring constants are. And before I do anything quantitative, here's a spring that's rather limp. Doesn't take much force to stretch it quite a ways. Here's a spring that's quite stiff. I've got to apply a large force to stretch it even a small distance. This spring has a much greater spring constant K than this spring. If I want to get quantitative about it, I've got a Newton scale here that measures force in newtons. I've got it set so that the weight of a spring on it will bring it to about 0. So here's this nice red spring. And the bottom of the spring is at the 20 centimeter mark on this meter stick. And I'm going to pull it another 10 centimeters. That's a tenth of a meter. And so down it goes till it's at about 10. And the scale reads about 4.5 newtons. So that was 4.5 newtons to stretch the spring 10 centimeters. That means the spring constant is 10 times that, because to stretch it 1 meter, it would take 45 newtons. So this spring has a spring constant of 45 newtons per meter. And if I double the stretch, just to see if that makes sense, it's coming up to approximately double the amount. An ideal spring, the amount of stretch and the force are directly proportional, the stretch being measured from whatever the spring's position is when it's in equilibrium, when it hasn't got any stretch in it. Here's another spring, this green one. It's the same length, but it's made of a slightly different wire. So if I stretch it 10 centimeters, wow, it's 7.5 newtons. That was a tenth of a meter, so this one has a spring constant of 75 newtons per meter. Finally, this white spring, with a little bigger diameter, stretch it down there. It's up to about 7.5, it's about 75 newtons per meter. So this K thing that you're going to see in the mathematics of springs is a measure of how stiff the spring is, how much force you get for a given amount of stretch. Newtons per meter are its units. So let's take a look at spring forces. And I've got a little movie playing here which shows a bungee jump. We won't pay a lot of attention to that, but I want to point out that a bungee cord is pretty much a spring, although bungee cords are designed so that they aren't exactly linear. It isn't exactly the case that the force is directly proportional to displacement. So we'll watch the bungee jump. The bungee jump is stretching, and the forces are getting greater as it stretches, and so on. Well, here is the force versus distance curve for an ideal spring, one that obeys what's called Hooke's law, one in which the force of the spring is directly proportional to the stretch, x, and here the proportionality is that spring constant k that we were just measuring. And because it's a direct proportionality, the force distance curve is a straight line. We've just seen that the area under the force distance curve is the work done in stretching the spring or in exerting a force over a given distance, in this case to stretch the spring. And we can calculate that area because it's simply the area of this triangle. And you can see that the area of this rectangle would be kx times x, but the area of the triangle is 1/2 that. You can see this half is not under the curve. And so the area under that curve is a half kx squared. So that's the work we do if we take a spring and we stretch at a distance x from its equilibrium position. By the way, if it's a spring that can be compressed, it's also the work we do if we compress at a distance x from its equilibrium. So the work is the triangular area. It's a half kx squared. It's the area under the force distance curve for a spring. So that's a useful thing to remember about springs. A half kx squared is the work it takes to stretch a spring by a distance x. I want to ask a question about what happens when I do work on something, like stretching a spring, like lifting a bowling ball, whatever. Let's do some examples. So here's a bowling ball. I take the bowling ball and I lift it. What happened to the work that I did? Well, if I lift it right over my head, when I'm in the classroom, I usually do this to a student, I should be worried. Why? Because this bowling ball has the potential to fall and do me grievous harm to my head. In some sense, the work I put in by going, and lifting the bowling ball is available to come back and get me. In fact, it can turn into the energy of the ball's motion as it falls. The force of gravity can give back work that got done against it. That's what I'm saying. Similarly, if I take the spring and I stretch it, my face is now in danger if I were to let go of that spring, because the work that I put in stretching that spring is somehow stored in that spring and come back and get me. We call that stored work potential energy. It's potential because it's not doing anything right now, but it has the potential to make, in particular, motion. So the idea of work is closely related to this idea of potential energy, energy that's been stored as a result of doing work on something like a spring or a massive object lifted against Earth's gravity. Now, there are other forces we've dealt with. There is, for example, the force of friction. I was very worried when I lifted the bowling ball over my head. I had good reason to be worried. But should I worry about this? Take this block and push it. I've done work. Because I'm exerting a force over some distance, I'm doing that work against the frictional force. If I let go, is that block going to come flying back and hit me? Of course not. I don't have to worry about potential energy with that force. That's a different kind of force. In a fundamental way, that force cannot give back to me the work that I've done against it. What happened to that work? Well, if you really want to know, it went into heating up this table. And that heat is sort of gone. I can't recover it as motion of that block. So there are evidently two different kinds of forces. And the two different kinds of forces are called conservative forces and non-conservative forces. And we've just seen examples of them. Conservative forces give back the work that's done by pushing against them with forces. Gravity is an example of a conservative force. The electric force is an example of a conservative force, as we'll see when we get to electricity and magnetism. Elastic forces, that is, forces of springs, are approximately conservative forces. There's a little bit of loss of energy in this spring when I stretch it, so it doesn't give back quite all the energy I put into it. But elastic forces, like spring forces, are approximately conservative forces. The work done against these conservative forces gets stored as potential energy. Then there are non-conservative forces. They don't give back the work that's done against them. Friction is the paradigm example of a non-conservative force, but there's also air resistance, which dissipates energy in the same way. The so-called viscosity of fluid is a non-conservative force. They produce heat rather than storing and then giving back the work that's done against them. So there are two kinds of forces, conservative forces and non-conservative forces, and what they do is produce potential energy if they're conservative, and they only produce heat if they're not conservative. So let's look at potential energy. Potential energy is this stored work I've just talked about. In the gravitational case, if I lift a mass m and I lift it a distance h, well, I've got to apply a force equal to its weight, mg, and so the gravitational work I've done is mgh, and that's the energy that then gets stored in that object that I've lifted. So when I lifted the bowling ball over my head, I stored energy equal to its mass times g times the height through which I had lifted it. We'll use the symbol U for potential energy, and so U subgravitational is simply mgh. What about the elastic potential energy when I stretch a spring? Well, I worked that out. That's what we've got on the big screen here. We found out that work was a half kx squared, so that work ends up being the stored potential energy when I've stretched or compressed a spring. So the elastic potential energy, delta U elastic, is 1/2 kx squared. By the way, I'm writing deltas on both these U's because the actual value of potential energy never matters. We sort of arbitrarily define a zero of potential energy. Maybe when this bowling ball is sitting on the table, I call that the zero of potential energy. And then how much more potential energy did I put in? Or maybe I could call the floor the zero of potential energy. It doesn't matter. So we'll be writing delta U for changes in potential energy. And the change in potential energy associated with gravity is mgh, at least gravity near Earth's surface. The change associated with a spring is a half kx squared when you stretch the spring from its equilibrium position. In general, the work done by conservative forces, if you take the negative of it, you get the change in potential energy. Now, what's that negative sign about? It's about when I lift the bowling ball, for example, gravity is doing negative work on it because gravity is pointing downward and I'm moving it upward. The work, the change in potential energy, is the work I do, and that's the negative of the work done by the conservative force in question. In that case, gravity. In the other case, might be a spring. Okay, now I want to get to the really big ideas I mentioned at the beginning of this lecture. I want to talk about what happens if I do work on some object, and I want to look in mathematical detail about what goes on. And before I've been talking about just the work I might do in lifting the bowling ball, now I want to talk about the net work that gets done. The work that gets done by the vector sum of all the forces that are acting on the object. So here's the issue. Suppose I've got an object subject to a constant net force. It starts at some speed, which I'll call v1. I move at a distance delta x, and at the end of that distance, it ends up at some speed v2. And in the process, some work has been done, and the net amount of work, that is the work done by the net force acting on the object, is w. So the net work done, w, is the net force times how far I moved the object. But I know Newton's second law. Newton's second law says the net force is the mass times the acceleration. Well, that's the mass times the rate of change of velocity, delta v divided by delta t. So the work, the net work I've done is the force times the displacement. The force is ma, so there's mass times acceleration, delta v over delta t, and that was multiplied by delta x to get the work. And I can rearrange that a little bit algebraically. I can put the delta x over the delta t and the delta v out in front. And what's delta x over delta t? Well, that's the rate of change of position. That's the velocity. So delta v is v2 minus v1. Delta x over delta t is the average velocity. That's v1 plus v2 divided by 2, as we found way back in an earlier lecture. So there we have a new expression for the work that was done. So if I work that all out, delta v is v2 minus v1. The average velocity is v2 plus v1 over 2. And so from Newton's second law, we have the net work I've done is the mass times the difference in velocities times the sum of the two velocities starting and ending divided by 2. Now, remember from high school algebra, or work it out by just multiplying the terms in parentheses here, a minus b, which is sort of what I've got here, v2 minus v1, times a plus b, v2 plus v1, ends up being a squared minus b squared. You learned that in high school, but you can also work that out. So the net work involved is 1/2 mv2 squared minus 1/2 mv1 squared. And that tells us something very important. It tells us there's some new quantity we need to think about. 1/2 times the mass times the square of an object's velocity. And that quantity changes if, and only if, work, net work, gets done on the object. We call that quantity kinetic energy. That's the energy associated with an object's motion. Kinetic energy is 1/2 mv squared. Where did that idea come from? It came from Newton's law. It came from Newton's second law. This was applying Newton's second law to find the work done in moving an object with a net force as its velocity changed from v1 to v2. So that's the net work done on an object subject to a constant net force starting at some speed and ending up at another speed. And although I assumed the force was constant so I could apply Newton's law without having to do calculus, this is in fact a very general result. And the general result is called the work energy theorem, and it says that the change in kinetic energy, capital K will be our symbol for kinetic energy, is equal to the net work done on an object. Very simple result called the work energy theorem, very powerful, and it follows from Newton's laws. It's part of Newtonian physics. It has identified for us this new quantity, kinetic energy, and it said there will be a change in kinetic energy of an object if and only if there is net work done on that object. As advertised, we've come up with a number of big new ideas. We started out with work. From work, we developed the idea of potential energy. We also developed then the idea of kinetic energy and kinetic energy in relation to work through the work energy theorem that says the net work done on something is equal to the change in its kinetic energy. A lot of big new ideas, all of them grounded basically in Newtonian physics. But the biggest idea is yet to come. And for the biggest idea, we need to do just a tiny little bit more math in developing this principle. And this is a principle that will go beyond Newtonian physics. We'll be using this idea at the very end of the course when we're way deep into modern physics and quantum mechanics and so on. This is the principle of conservation of energy. But let's see rigorously where that principle comes from. It's a huge idea in physics. It's used throughout physics, the idea that energy is conserved, that energy can change form, but energy can't disappear. It's like matter. It's one of the big stuffs of the universe, one of the big substances that makes up the universe. So where does the idea of energy conservation first arise in physics? Well, we just worked out the work energy theorem that says the change in an object's kinetic energy is equal to the net work that gets done on an object. If you don't do work on an object, its kinetic energy won't change, and because its kinetic energy is a half mv squared, that means its speed won't change either. The work energy theorem equates the work done on an object, the net work, with the change in its kinetic energy. We've also looked at potential energy, and I mentioned that potential energy is the opposite, the negative of the work done by conservative forces. Now, it might have been easier to think of potential energy as the work I do when I say lift the bowling ball or stretch the spring. But because of the emphasis on conservative forces here, conservative, the same word at the root of conservation, we want to talk about the work done by conservative forces. So when I stretch the spring, I do work on the spring, and the spring does negative work on me, and it's the negative of that negative spring work that becomes the positive potential energy change. That's why there's that minus sign there. So the change in potential energy is minus the work done by conservative forces. I can rearrange that to say the work done by conservative forces is minus the change in potential energy. And now comes the big step. If only conservative forces act, gravity, electrical force, to a good approximation, spring forces, but not forces like friction and air resistance and fluid viscosity, then the net work is the work done by conservative forces. Now there's a big step there. This does not always have to be true. But if it is true, if we have only conservative forces acting in a system, then the net work will be the work done by conservative forces. And in that case, delta K will be the work done by conservative forces, the change in kinetic energy, and that will be minus the potential energy change. So we'll have this expression, the change in potential energy, a change in kinetic energy is minus the change in potential energy. Let's do a tiny bit of algebra on that. Pull the delta U to the other side where it becomes positive, and we have delta K plus delta U equals 0. And that is a great big statement. That's the statement of conservation of mechanical energy. That says if there's a change in kinetic energy, say the kinetic energy goes up, then the potential energy has to go down accordingly. If the potential energy goes up, the kinetic energy has to go down accordingly, such that the sum of the two, the kinetic energy plus the potential energy, does not change. When only conservative forces act, the total energy, K plus U, kinetic energy plus potential energy, doesn't change. And there's an important adjective in there. It's the adjective mechanical. Mechanical energy is the sum of kinetic energy and potential energy. It doesn't include the kinds of energy associated with, for example, heat. Those are energies we begin to worry about when non-conservative forces act. When I pushed the block across the table, non-conservative forces acted and I got heat. But in a system in which only conservative forces act, or to a good approximation in a system in which friction is very small, for example, then the sum of the kinetic and potential energies doesn't change. But I can convert kinetic energy to potential, potential energy kinetic, and back and forth as long as I keep the total energy constant. Let me end with a beautiful illustration of this interchange of forms of energy. So over here I have a nice big yellow ball. It's suspended from a spring. It's supported by the spring against gravity. If I set it into motion, a motion, by the way, we'll study in mathematical detail in Lecture 17, It is exchanging energy among three different forms: the elastic potential energy of the stretched spring, the gravitational potential energy associated with the ball's height, and the kinetic energy associated with the ball's motion. At the top of its trajectory, it has no motion, it's all potential energy. At the bottom of its trajectory, it has no motion, it's all potential energy. Somewhere in between, it's moving rapidly and has significant kinetic energy. There are interchanges going on between all three of those forms of energy as this ball moves, and yet, to a very good approximation, neglecting air resistance and losses in the spring, the energy, the total energy, the sum of the spring's potential energy, the gravitational potential energy, and the kinetic energy of motion of the ball stays constant. We're going to see that that great big idea pervades physics from now on way into modern physics at the end of the course. And in the very next lecture, we're going to see how that idea allows us to solve problems in physics that would be very difficult to solve just using Newton's second law.